So I welcome everyone to this last day of training. I imagine that it can have been a tough week, a very crowded week and full of stuff. I hope it will be not so difficult to follow today. The topics that we are going to face today are, let's say, exploiting all things that you have learned in these days. So I hope that it will be also clear why they can be useful and which are some of the possible applications that they can be dedicated to. So please, let's make this as much interactive as possible. So please let me know if something is not clear, or if you are more interested in deepening some topics. I will start sharing my presentation. So the topic of today are Copernicus Emergency Management Services and crisis maps production. So these services exploit the use of satellite imagery, satellite image processing, as well as GIS data processing. So that's why you should be able to put in practice everything that you have learned so far. Sorry. So let's start with the Copernicus Emergency Management Service, just an introduction to this service which is provided by the European Commission. As you have probably learned already in these days, and maybe you knew already, Copernicus is a huge program of the European Commission providing observation of the phenomenon of the Earth and also analysis of data to monitor these phenomena. Copernicus EMS is only one part of the Copernicus program, which is dedicated to emergency management. And also Copernicus EMS itself is composed by different types of services that we are going to explore today, focusing more in the upper part of this figure. Let me change the pointer. So Copernicus EMS in general is dedicated to provide information for emergency response and disaster risk management. So in order to provide support for all phases of emergency, probably you know that emergency have different phases, starting from preparation to facing the emergency itself, to recovery, and again to be prepared to better face or possibly avoid a future disaster. So the idea is to support all these phases with different types of products. So we find here in the top part the on-demand mapping service, which is divided into two sections, which is the rapid mapping and the risk and recovery mapping. And in this second part, we have the early warning and monitoring. So these services, which will be introduced in the end this morning, will be dedicated to monitor some phenomena, but possibly also alerting when these phenomena are about to occur. For example, there are some phenomena such as floods or fires, which can be linked to specific meteorological conditions. So monitoring the critical meteorological conditions, it is possible to alert the municipalities which could be affected by a disaster in a short time. And also the aftermath of the disaster is monitored through these services, which we are going to briefly introduce at the end of this discussion today. But the first part of the first part, yes, of the service, which is the on-demand mapping, is the one that we are going to dedicate the majority of time. What is on-demand mapping? It is a service which is provided in particular to civil protection, but not only. The idea is that Copernicus is offering a free service to authorized users for having available maps in case of disasters. This is in particular what is dedicated to rapid mapping. Why rapid mapping? Because if you have a disaster, you have the opportunity to monitor it with satellite imagery and to have information about which is the impact of the disaster over a certain area. And exploiting satellite imagery, you can see how large is the affected area with a fast processing of satellite imagery. Instead, of course, having the same information from the field could take much longer time. Related to this, we have also risk and recovery mapping. I told you that the idea is that this service should provide support for all phases of the emergency. So also the following phase of the emergency, which is the recovery one, or the risk assessment. So to see what could be affected by the disaster in case it occurred. So the pre and the post event phases. So that the users, the civil protection and the other actors who are managing the emergencies can have support for their planning and their design of activities. So these are the two types of maps which are planned. So the idea of the rapid mapping is that these maps should be provided in a very short time after a disaster occurs. Imagine that there is a flood event. It is of interest to know with the best possible approximation, which is the extension of the flooded area. It is possible, exploring satellite imagery, to delineate, to draw which is the flooded area. So this is provided upon maps that are distributed freely for the users. Of course, every citizen is paying for that, but free for the users in order to plan their activities for facing the emergency. Same principle for risk and recovery maps, but in that case, no need for rush, in the sense that these maps can be produced over several days. It's not requested to do them in a very short time right after the emergency. Now we are going through these services, these types of maps, one by one, in order to understand what they provide, and how they are produced. A short introduction about the workflow of this procedure. Here you see a very complex schema, but we are not interested in going into the details. The idea is to give you an idea on how, which is the process for the production of these maps. We said that we have the end users, which are authorized users. I mentioned already the civil protection, but there are also other authorized users, like, for example, the World Food Programme or other international ONGs or international organizations which have of interest the health of people. This service is provided by the European Commission, but it's not dedicated to Europe only. So it is possible, as I said, for organizations which are active all over the world to activate it also for other countries which are not European. But if you will see if you take a look at the activations of the service, you will see that the majority of the activations are for Europe. So in case of a disaster or in case of the need of maps, because as we said, the idea is to support also the other phases. So imagine that you know that there is an area which is prone to flood or prone to fire, forest fires, for example. It could be that the operators in the field have the feeling that the maps that they have for planning their activities are not enough. So they could trigger the service even not during an emergency, but in advance to say, I need reference maps for or risk maps for this area because a flood could occur and we have not mapped that part enough. And this happens in particular in developing countries where the maps available maybe are not enough. But let's consider, let's say, the most common case, which is the case of an emergency which has occurred. So we have that something is happening, a flood is happening or a fire is happening. So imagine that the civil protection contacts the point of contact of the service, asking for the production of maps. They suggest which is the area of interest that they need to be mapped. Then there is the service which makes a first evaluation of the request. And if the request is accepted, then there are other phases that are very important. The first one is the satellite image acquisition, because you have learned now that we have satellites observing the Earth and that we have different types of satellites observing the Earth with different types of information that can be provided. In case of a disaster, we need to acquire a proper information which allows us to extract the data that we need with respect to the disaster. So depending on the disaster, we could need different types of images. You know that the satellite has a certain revisiting time, so it passes over a certain portion of the Earth every certain days. And if we want to map a disaster fast, we need that the image is acquired as soon as possible. So we cannot wait 15 days. In 15 days, the emergency could be over, or at least in a phase for which the map is not needed anymore. So we need to find a compromise between the best image that we would like to acquire and when it will be acquired. In addition, there could be limitations to the acquisition, because if we use optical imagery, so the satellites that you have learned with Professor Gianinetto, which observe also in the visible portion of the spectrum, you have that images can be covered in clouds, in the sense that with an optical sensor, if the area is covered in clouds, what you see on the image is clouds. And with that, you cannot do very much. You cannot see what you have below. So it could be another slowing factor for acquiring images which are suitable for producing the maps. So a compromise and a planning must be done, also checking the meteorological conditions in order to acquire the best suitable image in the shortest possible time. And this is usually the phase which is requiring longer when we are trying to produce these types of maps. This phase could take from few hours, if you are very lucky, to 2 to 3 days. Usually no more is required, because luckily we have different satellites exploring the Earth. You have focused your attention on Sentinel satellites, which provide images for free, but Copernicus service does not rely only on those images. They can also buy satellite images from other services, so that they can rely on more satellites and are able to get the images sooner. Once that the satellite image acquisition is triggered, we can wait for its acquisition, and then it is delivered to the map providers, who process the images in order to extract the needed information, then the maps are quality controlled and the maps can be delivered to the users. So you have seen that I have simplified very much this schema, but the important phases are the ones which are summarized in the text in the left part of the slide. Once that the maps are produced, they are shared with the users also through the web service of Copernicus EMS, which you can access. You have that on the website. You can see the latest activations of the service. You can see that they are not only in Europe. We have here also South America, Africa, and also Australia. You see here from the icon which type of emergency watch was mapped. Here you see also the list of the latest Copernicus EMS activations, but you can access also here from the list of activations all past activations, also which can be queried in order to find the products that you can be interested in. All maps are downloadable for free. All maps are shared unless there could be some security reasons. Imagine that some maps are produced in case of a conflict between two countries in order to avoid difficulties for politics or for security. In some cases, these maps are not shared. Otherwise, they are always shared with everyone for free over the internet. Now I'm discussing this, let's say in theory, but this afternoon with Juan Fernando Toro, you are going to explore this and to use these maps in practice. So to see how they are and how they can be used. And you will have also a small exercise to understand how they can be produced. Once they are produced, as I said, they are shared over the internet and they are shared in different formats. They are shared in raster format and in vector format. In raster format, they are in, you see here a screenshot, but we are going to see it better in the next slides. This is called printable map in the sense that it's a map which is not only in raster format, but it is a raster format which is designed to be printed. Instead, the vector format is expected to be loaded into a GIS software in order to be used with other layers that probably the users have already available. So imagine, for example, that you have the perimeter of the flooded area and you are a user of the municipality who has already all detailed maps, the plans, maybe also the evacuation plan, and so you can overlay the flooded area with respect to other maps that you have already, so that you can better plan the activities directly into the GIS software. Usually, here you see only 200 dpi, but usually the printable maps are provided in different resolutions, also 100 dpi and 300 dpi's, for example, because it could be that the conditions during an emergency do not allow to download very large files. It could happen in developing countries, but not only. Imagine that you have an area which has suffered a severe earthquake or a severe flood, which could have cut some of the connections. So the networks could be worse than usual. And so in order to provide the possibility to download the images even fast and with a bad connection, they are provided with different types of resolutions. You will see that when you deal with an emergency, you have to take care of many details that are different. I remember once there was a person from the World Food Program who is used to work in developing countries, who said that these maps, which are usually meant to be printed in large format, let's say A3, A0, A1, had to be printed on an A4 printer because it was the only one available, maybe in a developing country with an emergency. And when you shrink it to A4, then it's not as visible as it was designed. So in the field, they had problems managing it. So when you work with emergency situation, you have to design things in a different way. I would like to spend two words saying why I work on this and where I acquired this experience. I had the opportunity to work at the Joint Research Center of the European Commission for 2 years during a postdoc grant. And I was working exactly on a pre-operational project with respect to the Copernicus EMS rapid mapping service, how it exists right now. The service exists since 2011, 2013, 15. It had different phases of starting, but it existed even before. There are also other services other than Copernicus EMS. There is UN, who has a service for rapid mapping. There is also International Charter, who is another international, let's say, group working on this task. But as I said, also this service had some, let's say, pre-operational phases in which the characteristics of the service were tuned. And I was in the team for the validation of the crisis maps, which were produced at that time. And it's where I acquired experience about these maps. And I had also the opportunity to talk to people who worked in the field, because I had to go in the field for validating the maps. So it's something that I haven't learned only, let's say, on books. I had also a direct experience about this. And now let's say that these types of services are becoming more popular and more known, and also wider, because they are including also the contribution of people. Also, Copernicus EMS is studying the opportunity of exploiting the fact that every person has a smartphone, as every person is sharing information. So this information coming from the field can be exploited in such maps, because of course the direct experience of people who are there could be very valuable for providing additional information to such maps. Of course, this is not so easy. That's why it's something that is still under study, because people could be reliable or not. The position of the data could be precise or not. We cannot directly ask to people to go and map the emergency, because we could put them in danger. So there are limitations to these types of conditions of exploiting crowdsourced information, but it's still something which is of very much interest, because it has been already done to exploit the data coming from people from the field. And it's a very valuable source of information. Another thing that I would like to say is that the contribution of people in general and the crisis mapping in general has had a sort of turning point with the Haiti earthquake of 2010. I don't know if you heard about it. It was a huge earthquake which had many losses, because it was in a very poor situation where there were many slums, so houses which were not really houses, which were not even buildings. They were slums with very poor conditions, which were very much unstable. So they had very serious damages after the earthquake, which was very strong. And many people died, many people were affected. There was a huge contribution from the whole world. And one of the things which was discovered immediately was that the area was not mapped. There were no adequate maps for that area. And to overcome this, huge community moved to map that area. And in very few days, volunteers from all over the world exploiting OpenStreetMap, which I think it was introduced to you during these days, I hope so. If not, please let me know. Was mapped very fast over Haiti. So in few days, the OpenStreetMap of Haiti started from being completely empty to be very detailed, thanks to the exploitation of satellite imagery and thanks to the exploitation of the contribution of common people. So Haiti earthquake of 2010 was really a turning point for all activities which are around mapping and around emergencies. And also the crisis map production was pushed even more after that event. Now we are going to explore these maps a bit more. In these slides, I'm going to show you a bit how to read this printable map. This is an example of a rapid map for a flood event. We are going to see what is this text that we have here on the right side of the image. Let's see what you can find here. And again, if you remember what you have learned in the past days, probably some of you maybe are geography teachers, so maybe you are very much aware about this, but these are details which are in the good practice of preparing a map. For a printable map, it's easier because you have a space where to write the text. In case that you have only a vector layer, you need to provide this information into the metadata. Because one important thing that you should consider when you use digital information and digital geographic information is that to use it properly, you need to know its characteristics. So it's not that I have a map and knowing that I have it is enough. I need to know when the map has been produced, by whom, if it has been changed by someone else, which processing it has been done, which is the resolution, which is the level of detail of the map. So in case of the printable map, we can find all that details into a text. In case of a digital map, in the sense that a vector map or a raster map where only data are provided, you need to check this information into the metadata that must be properly completed and filled. So here you see some details about the event. So when the event occurred, no, actually this is not when the event occurred, but when the map has been produced. And as we will see, for a flood event, it's really important because the flooded area can change over time during the event. Codes of the map, because often more than one map is produced, so you should know which portion you are watching. The area of interest, and the area of interest should be showed also on this overview map, so that you see where you are in the world, because it's not mandatory that you know where this city is. Then you have the information about the maps. This is the scale, which is valid only if you print it in A1 format. Of course, you can print it at a different scale, but the level of detail and the the map is not designed to be printed at a different scale, so you should be aware about that. This is the scale in the form of scale bar, which can be adjusted with respect to the size of the printing. What you should always remember is that the level of detail and the characteristics of the map are linked to the original scale and not to the one that you could be adjusted to. Is there a question? No. Okay, then you see the representation, which is WGS84 UTM and the zone. This is really important, and this is the most common one, as you probably have seen. So WGS84 ellipsoid is the most used one, and the UTM representation is as well one of the most used, because it can be applied everywhere in the world with simply providing the code of the zone that we are considering. Here you see the legend. The legend is really important. I can tell you shortly about an experiment that we did when I was working at the JRC. We showed some maps to experienced users, so to civil protection users, so people who were used to these maps. And we used a tool for measuring their where they were looking. So there is this eye tracking tool, which allows you to see where we are looking, and it is a tool which can be used for many purposes. Usually, it's not used for analyzing maps. Usually, for example, it can be used for the supermarkets to see where people look more. So which are the shelves that are more targeted by people, so that they can put there the products that they want to be sold. But we applied this technique to the map readability, and we have seen that many people, the majority actually of people, didn't look at the legend at all. And given that, as I said, probably some of you are geography teachers, you know that this is not a good habit. Given that in the legend you have the code of the map, it's necessary to see which is the code of the map in order to be able to interpret it. It's also true that some of these codes we are used to. So that's why it is important when you produce a map to put a code which is easily understandable and which is, let's say, intuitive. For example, that you have red corresponding to something which is critic and green corresponding to something which is safe, and not the opposite. And this is something also that I teach to my students, and sometimes it's not so easy to obtain it to them because they want to use colors that they like. But if we make maps which are designed for emergency management in some way, we need to use a color code which is easily intuitive. So it's very important to check how the data are represented on the map, and you can see here, for example, that we have two shades of blue represented the two different times of flood. So we have a flood situation of 13th of February and another situation for the 15th of February, and also all the other symbols that are used to represent the other elements in the map. Sometimes in these maps also an estimation of what's happening, of what has happened in terms of impact of the event you can find. So which was the extension of the flooded area, how many people were affected. Of course, this is an estimate based on the knowledge about the buildings which are over the area which is flooded. So here you can see how you could use the flooded layer, the layer of the flooded area, in order to extract additional information. And this is an exercise that you are going to do this afternoon in order to exploit this data for extract additional details. Other details about the transportation network which was affected and the other facilities which were affected. Here you see some details about the event. So when the event occurred, so it occurred very much up before the image acquisition. If you remember, here we had that the situation is at the 15th of February, while we see here that the event was from the 6th of January. So it was a flood event which lasted very much. This is not what is called a flash flood. When you have a flash flood, you have that the water is coming very fast and going away very fast. In this case, you have that the water is staying for much, much longer. Here you have details about the area of the town, and which is the scale of the data that were available, and also which is the estimated geometric accuracy. So you expect that the level of detail, the positional detail of the elements of the map have a 10 meters accuracy. So this is very important with respect to maps, to know which is the positional accuracy. So if you read the coordinates of them on the map, how close they can be in the field. So 10 meters is not so bad, but imagine that 10 meters could be that a building is not in the right place if it's a small building. Of course, if you have a large building, 10 meters is not so much, okay? And then the date records with respect to the event, the activation. So you see that it was activated 1 week after the event itself, when the image was acquired and when the map was produced. So only 1 day after the image was available. Here we have additional information with respect to the data that were used for producing this map. As we will see, we are going to discuss all day, all morning about these types of maps. So we are going to provide details about it. But usually what you do in order to be able to produce these maps is to compare a pre and a post-event image. So here you see which images were used to produce this map. And you see that a pre-event image has been used, which was a Sentinel-2. Actually, both Sentinel-2A and B were available. And I don't know if you could get this information. A and B are both SAR and optical images provided by Copernicus. Post-event RadarSat, you see here, this is not a satellite which is provided by Copernicus. This is not free imagery. When it was acquired, and which is the GS distance for ground sampling distance. So it's in practice the geometric resolution. So the smallest element, which usually we call pixel, of the image has a size of 5 meters. So this is the smallest level of detail that we can have over the image. Then also other base vector layers were used. You see that OpenStreetMap has been used, Wikimapia also, which is a platform for providing free maps similar to OpenStreetMap. We have GeoNames, which provides topographic names about all places in the world. Corin Landcover, which probably was mentioned to you, which is a land cover produced by the European Commission for free every few years, so to monitor the evolution. This is automatically produced, so it contains errors, but it is a very valuable reference. Also the global administrative areas and so on. Where it comes from the population data and so on. Here you often have a disclaimer in these types of maps, which tell that the map is produced based on satellite imagery, which doesn't allow to see everything, okay? From the satellite, as we will see in detail in the next slides, you cannot see whatever. There are limitations. So you can map what is mappable, let's say, from the satellite imagery. The details which are not visible are not mapped, and this disclaimer says that this is not a fault of the map producer, but this is a limitation of the data. So this is how the map should be taken. And this is as well something which is very important when you work with maps, which is similar to what I said before about quality, about the legend, about the metadata. because every map has limitations. These limitations can be large or small depending on the type of map. What is important is not that the maps should be error-free, because we cannot have it, we know it. What is important is that we know which are the errors, so that we know how we can use this map and how we shouldn't use this map. This is what is, let's say, most important. Let me just check one thing. Okay. These limitations are very well known, should be very well known also to the users, so that they know how not to use this data, so not to use it in an appropriate way. I had the opportunity to discuss with civil protection operators more than once over these years, and apart from very rare cases, they said that these maps, despite all these limitations, were very useful during the emergency activities, because they printed these maps, they put it on the table, they were around the table discussing how to manage the emergency. If you see the civil protection crisis rooms in the field, they have maps printed everywhere on the walls, on the tables, and they use these maps for planning their activities. So despite the fact that we know that they have strong limitations and there are many errors, they are still very much useful, and that's why they are still produced and used very much. Of course, the technology is improving, the processing techniques are improving, so we try to overcome as much as possible these limitations. But what is present, it's enough to declare it and to know it. Okay. Do you have any questions so far? Okay, I would like to go through the types of products which are provided by Copernicus. Again, I told you that more than one service exists with respect to these types of data. We are going to talk about Copernicus because we are in Europe, and also this project is funded by Europe, and probably also Copernicus EMS is probably the largest service providing these types of data. And it is also very well coded, so we have the types of products, we have the guidelines, so we know very much about these types of products. But as I said, they are not the only ones. We are going now to list which types of data are provided by Copernicus with respect to how they categorize them. So here we see an example of reference product. These are data which could be or not provided during the emergency, but this is not going to describe the emergency. This is going to describe the area of interest. So in case that we know that something could occur, or in case that we need reference data because we need to deal with an emergency, but we feel that the maps that we have are not detailed enough, it's possible to ask for these reference products, which correspond basically to a regular map with the details which are needed for the area of interest. So usually you have topographic information. Here you can see the buildings. Here you see that the background is again a satellite image. In my very personal opinion, this is not the best option, but this is very much the practice. So it's very likely that the background of these types of map is anyway a satellite image, even if I mean, it's intuitive for some reason, because now we are used to look at them, so we can recognize that this is woods and this is fields and so on. But first of all, you need a bit of a trained eye to interpret this. In addition, sometimes the details can be confused. So in my very personal opinion, I think that the best possible map is an interpreted map. So a map that I have produced only with the details that I feel that are needed. So if I want to specify that these are fields, I put a code for that. If I want to specify that these are woods, I put a code for that. The advantage of using a satellite image as a background is that you have the immediate feeling of everything. So the map is filled with details without the need of drawing everything. So here you see the boundary between one field and the other. If I wanted to map this, I should add lots of details in my map, which could be very much time consuming. So it's understandable why they prefer working like this. In the very last release of the guidelines of Copernicus, we have this the introduction of the first estimate products, or FEP, which is a product which should be provided, I think, 1 or 2 hours after the satellite image is available. So we said that the availability of the satellite imagery is the first step, which we cannot do anything about, apart from trying to choose the best option among the available satellites. But apart from that, we can only wait that the image is available. But once that the image is available, it's up to the map provider to do its best effort to provide the map fast. So this first estimate product is required to be produced in 1 to 2 hours. So, but it is also known that it is a rough estimate, just to say, okay, this is the area of impact without delineating it with detail. Because imagine that apart from the processing, you need also to produce the output, okay? So this is how it is represented. So you see the area of interest, you see the layer, which is very fast produced. It is known that this contains even more errors than the following products, but it can be used. It can be used for the early stage of the emergency, or it can be used to highlight which are the areas that should be mapped with higher details in the following phases. Okay, so this is why this product was introduced. Then we have what is called the delineation product. So delineation product means that the purpose of this map is to show which is basically the perimeter of the area which is affected without measuring the level of damage. So here we see an example of delineation map for a fire. So you see that we have only one color representing the burnt area. This is a fire in Australia. And this is what we call, as I said, delineation. So the perimeter of the burnt area in this case, without grading it. The opposite is what is done by the grading product, in which the level of damage should be estimated. And actually this is quite challenging with respect to the map production, because in this case, it's not always easy to say which is the level of damage. In this case, it's probably the information coming from the spectral response of the vegetation. So where the spectral response of the vegetation is still intermediate between dead vegetation and healthy vegetation, and we can say that it's destroyed where the level of damage is higher. So the information about the spectral response of the vegetation is lower. So the vegetation is not responding. So you see here that the difference is that we have still the perimeter, but we have the perimeter discriminated with different shades, from possibly damaged to destroyed. And actually the colors, I mean, we should zoom in, but the colors, you see that destroyed is only in a few areas. And again, when a map is produced, the contrast between the colors should be produced in a way that it's easier to discriminate among them. Let's say that between this medium red and dark red, I'm sorry, I was a validator of maps, so I have this eye of looking at the let's say the drawbacks of the maps, the limitations of the maps. I think that here the color choice was not the best, because it's very difficult to point out where you have the darkest color. Okay, so we have finished with the let's say introduction of what is the service from the point of view of Copernicus. We are now going into a bit of detail, because it will be a fast overview. We don't have time to go into the detail, but the idea from now on is that we are going to discuss how these maps can be produced. And in the exercises in the afternoon, you are going to see on the one side a very simple exercise showing you how they can be produced. So how you can manipulate satellite imagery in order to highlight the damaged area, and so to be able to map it. And on the other side, how you could exploit the damaged, the description of the damage, of the impact of the disaster, in order to make analysis about the impact not only on the territory in general, but for example on the population, so to intersect that information with respect to where people are, so where the buildings are, sorry, in order to be able to make analysis as if you were the user of the map, which is what I could suggest, for example, as a possible exercise to be done with your students for the following project. So if some of you could be interested, this could be one option for the project. So it could be to produce a map processing the satellite image, or to take the data provided by Copernicus for a certain disaster and to intersect this information with other available data, like the presence of buildings or the land cover, in order to see which is the impact over the territory in terms of population, in terms of land cover. So if the fields, the cultivated fields have been damaged, or if the woods have been damaged, and so on. Okay, so we were discussing about the crisis maps production. So first of all, what we said is that we are going to use satellite imagery, and in particular we are going to use pre and post satellite imagery to be compared in order to check what is what has happened in the area of interest. How to detect these differences between pre and post imagery? We do it exploiting semi-automatic processing, so exploiting some of the processings that you have learned in these days, but also using visual interpretation, so using the experience of the operator, who with the aid of the tools which are available thanks to the automatic processing, he can see which are the tools which are most suitable, and also he can set the parameters of these tools in order to detect in the best possible way the damaged area. Another important thing is that, if possible, the pre-event image should have the same characteristics of the post-event one, so that you can see objects that should appear in the same way because they have been acquired with similar characteristics of the sensor. And if they look differently, it means that something has changed in the field. Here we see an example of the pre and post satellite imagery for the 2004 Indian Ocean tsunami. So you see how the area looked before the event, where everything looked green, and what happened afterwards. Of course, this is not zoom in, so you can see only very much in general what happened. Of course, if you want to make a detailed map, you need to have a higher detail image, or to at least zoom in a bit, but to provide you with any idea of what it means to compare pre and post event situation. Today we are going to explore fast, of course, due to our time limitation, but I hope that this will be enough to provide you with a general idea on how this can be done, to see which are the data which are more suitable and which are the techniques that you can exploit for producing crisis maps for the different types of disasters. We are going to see what we should do in case of earthquake, fires, and floods. You are not going to make an exercise about earthquakes in the afternoon. You are going to make an exercise only with respect to fires and floods. Also because, as you will see, earthquake does not require any specific satellite image processing. It requires really only photo interpretation, so the ability of the interpreter to detect the damaged buildings and to draw them on the map. While for fires and floods, we can exploit also semi-automatic processing, which is, let's say, something that you have already seen during this week, of course. Let's start with the earthquakes. I have introduced this as well in the discussion, even if you are not going to map them, because I felt that it was interesting to complete the overview of the cases, even if you are not going to do it in practice. In this slide, you see the summary of what should be done in order to be able to map earthquakes. In case of earthquakes, what we are interested in is mainly the damage of infrastructures. So to see which are the affected buildings, and if there are debris in the roads, so if the road are not cannot be, let's say, you can go in the road because they are blocked by the debris, or if infrastructures are destroyed, such as bridges. In addition, in case of earthquakes, you could have side effects of other types of damages. You could have landslides, which are triggered by an earthquake, or you could have a flood, which is due anyway by an earthquake. It could be a tsunami, or it could be a river which is inundating due to a landslide. So you could have very different types of effects. But what we are talking about here is the building, how to map the building damage. You could have also the damage of buildings in case of events which are not earthquakes. As we have seen, we could have very severe tsunamis which have severe impacts on buildings. In that case, even if it's not an earthquake, you're going to follow the same principles that we are discussing here in order, sorry. I wanted to turn off the microphone, but it was not fast enough. So in case that we want to, what we are discussing here is mainly, as you can see here, building damage assessment, even if the damage assessment was not triggered by an earthquake. Okay, sorry. So in case that you want to assess the damaged buildings, what you have to do again is to compare pre and post satellite images. Here, maybe I could add here a line just to show better the difference between the left part of the image, which is the pre-event image, and the right part of the image, which is the post-event one. So the arrows are pointing at the same buildings, And here you see how they look like after the event. So you see that there is rubble, you see that they are misplaced. So you see that there are differences with respect to pre and post. What you can see also is that it's not so easy to detect it. Okay, so even if the pre and post event image are acquired with the same conditions, so you can easily see that it's the same sensor, the colors look a bit different because it depends on the sun conditions at the time of the acquisition. So you can see that apart from the rubble, which is easily visible, it's not so easy to interpret the damage. Okay. What should be done for mapping the damage is also to draw the polygons corresponding to the damaged buildings. And in case of destroyed buildings, this is even more complex. In order to be able to draw the polygon of this building or even more of this one, what you should do is to draw it on the prevent image, because on the prevent image you see how many buildings you had there and how they look like. This is not what you can do on the rubble. Okay, sorry again. Here you see, for example, a completely misplaced building. Here we can see the lateral facade. This was laying down due to the effects of the earthquake. But we discussed also that we have huge limitations from satellite imagery. There are some severe effects that we can have on structures which are not visible at all from satellite imagery. And here on the left side, you see an example. This effect is called the pancake effect or soft story effect. Here you see, I hope that you can appreciate that the first floor of this building is completely destroyed. In this case, it's only, let's say, not stable anymore. In some cases, one floor could completely disappear. This is a very unfortunate case which happened during the L'Aquila case, and very unfortunately into a residence for students, in which one floor completely disappeared. Of course, this is a very severe damage which compromises completely the structure. In practice, even if it's not yet destroyed, the building should be marked as destroyed. But of course, you cannot see this from a satellite unless you can estimate the height of the building, but this is something that rarely can be done. So you know that this is an extreme case because you have that from the field, it's evident that the building is completely compromised, but it's not visible from the satellite. But you could have even less extreme situations in which also this case, for example, here you can infer from the rubble around, but here you have that again, you have a building which, a floor which is compromised, or you could have that you have cracks on the walls, and these cracks on the walls could be severe, but you cannot see them from the satellite. So again, this is why we have this disclaimer, you cannot see everything. So you're going to point out only what is practically visible from the satellite image. An option, sorry again. An option which is available in some cases is oblique images. These cannot be acquired by satellites. These can be acquired by airplanes or UAVs, drones, if you want, unmanned aerial vehicles, which allows you to see at least the facade of the building. So watching the facade, you are able to see these types of effects or the cracks on the walls. And so you can map better the damage. Here the level of the, what happened? Sorry. Can you see me? Can you hear me again? Because I had probably an interruption in the connection.
Yes.
But it was restored likely. Thank you very much. So you can see here how, with respect to these guidelines, we should mark the buildings as destroyed, damaged, possibly damaged, or to mark as no visible damage. You see that the slight difference between no damage and no visible damage. So it's not that the building is not damaged, but I cannot see any damage from the satellite image. And so you see here how these have been classified. These pictures are taken from the central Italy earthquake, and actually you can see the roof of the buildings with very much detail, because these are not satellite images, these are aerial images, which have been used as a sample for best practices, because these allow to see many more details. Okay, sorry again. I'm very sorry. Okay, so we are not interested in the details of the guidelines. I have put them just if you are interested in checking them, and also because there are some figures of different possible situations, pre-event and post-event. Here you see, actually, you see that I was focusing on this. Here you can see the difference between the satellite image, the aerial image, and the UAV. So the even more detailed information coming from the unmanned aerial vehicle, so from the even a lower height, even that actually here the aerial and the UAV ones are very similar, but it depends on the flight height. So here you see how worse it can be, the visualization over a satellite image with respect to aerial one. Of course, here we are talking about an old village in central Italy affected by the central Italy earthquake of 2016. And in this case, the buildings are very small. So to detect the damages of very small buildings with so peculiar roofs is even more difficult on a satellite image. In case of much larger buildings, the situation is a bit better. Here I have put an example of a crisis map for, again, for the central Italy earthquake. Here you could recognize some of the buildings that were depicted in the previous guidelines. For Italian people who are maybe could be interested, this is Accumuli village in central Italy. And here you see how the damage has been mapped. So you can see that the perimeter of the buildings has been marked with different colors depending on the level of damage which has been highlighted. Okay, again, this is an aerial image, so you can see so many details because it's taken by a much lower height with respect to aerial imagery, satellite imagery. Okay, that's all with respect to earthquakes. It was very fast. I would like you to make a very short exercise just to stop a bit the talking if you want. I'm going to put a link in the chat in which you could try to make a simple exercise if you want, but this is not an exercise in terms of, let's say, image processing. This is only visual analysis. If you could go to this address with your laptop or with your smartphone, as you prefer. Wait a second. If you go please to this address, you wait that I can share my screen as well so that you can see what I see. These are two images. You remember that I mentioned the Haiti earthquake case. So these are pre and post event satellite images of Haiti earthquake, and these were GOI images with 50 centimeter resolution for each pixel. So in principle, this should be very much detailed, but as you can see, the contrast of the image is pretty bad, and it's not easy at all to interpret this. And you have also the perception of the fact that it's difficult to see the differences. So what I'm asking you is to try to detect the damage on the right image, which is the post-event image. So just to make this simple attempt of detecting the damage, comparing the pre and post situation. Could you access the, because it seems that nobody did. If you want, of course, if you're not interested, we could skip it. If you could try to access the address that I have put in the chat.
It asks for login.
Ask for login. It shouldn't. Actually, it's not really login. You can put whatever name, your name or a fantasy name, a nickname, whatever. It shouldn't be needed to log in.
It asks us for a code, and the code is the last.
Code is the last letters, yes, GPMGIS. But if you click on the link, actually, you should go directly inside. If I put the link as it is here, you should copy. Probably because I don't know why it has taken as a link only the first part of the text, but everything is a link. So if you copy and paste the link, including GPMGIS, you directly go to the. Okay, so you should try to depict the damage, to detect the damage on the right side, because on the left side you have the pre-event image. And correctly, you saw that there was something wrong also in the pre-event, but that's just because as I told you, in this case, in the Haiti case, the buildings were in very bad conditions even before. So what you see on the left side is, let's say, looks damaged, but it was not damaged, at least not by this earthquake, because unfortunately the area was affected also by other earthquakes. So it could be that there were damages from previous earthquakes which were not restored that. Or it could be, in some cases, there were buildings which were under construction, so you could not access them. You could not, let's say, they look as damaged even if it was like that before. So it's just to provide you with an idea on how difficult it can be. One of the reasons why we were requested to make a very fast assessment right after the Haiti earthquake, actually there were many assessments which were done by common people, by professionals. There was a very huge contribution by people after this earthquake in terms of mapping, as I already said before. And one of the reasons why it was requested to us at the JRC to make this assessment exactly with the images that you are using right now, it was because the World Bank needed a fast estimate of the number of buildings which were damaged, and also counting the buildings here is a bit of challenging, because they wanted to estimate how much money to send there. So they wanted to have a fast estimate, even if it wasn't, let's say, very accurate. I think that your estimate is pretty good. I had put these squares for showing which could be the affected areas, but it could be also that I was not correct in the sense that there is no reference in this case, so it's just how trained our eyes are with respect to the damage. So it could be that I missed something or that I overestimated the damage in some cases. Anyway, just to give you a fast perspective of what it means to make this exercise. That's why we didn't include it into the practice this afternoon, because this is only a matter of training your eyes and to really become a fast mapper, which is not the purpose of this course. So I included only this fast exercise in order to let you touch what this is. Okay, so do you have any questions, any remarks with respect to this? Okay, so we can go back to the presentation. Okay, now we stop talking about earthquakes and we move to talk about fires. This is more, let's say, related to what you have studied with respect to satellite images, and maybe is even a bit more interesting. You see a bit more the application of what have been explained in the last days. So you have learned something about spectral reflectance of the objects over the Earth. You have learned that depending on how the objects reflect the sunlight, we have that they have a different response in the different bands that we can detect with satellite images. In particular, you have seen that vegetation has a very peculiar response, which allows us to see evidently that if we can explore the bands which are not the same that we see with our eyes, so if we'll explore non-visible bands, we can see additional details. And this is visible also here in the spectral signature of a healthy vegetation, in which we see that vegetation has a small peak in green band. That's the reason why we see vegetation as green. But we can see also that we have a much higher peak in near infrared. So if we exploit this this property and we display the near infrared band on our screen, we can more easily detect where is healthy vegetation and where it is not. You have discussed probably with Professor Gianinetto the color composition, the fact that if you paint with red using as a brush your screen, so if we load the near infrared image and we color it with the red component of light over the screen, we can see that the vegetation looks red. Actually, it looks magenta, but it looks red. And in particular, we have that a healthy vegetation looks red. So the more the vegetation is healthy, the more it reflects green, but even more it reflects near infrared. This is linked to the presence of chlorophyll inside vegetation. So this helps us in detecting where vegetation is disappearing. So if the vegetation is dead or is dying, is let's say not healthy anymore due to a fire, we can see that the response of the vegetation to green is lower, but the response to vegetation to near infrared is even lower. Here you see an example of pre on, let me change again the pointer. You see here the pre-event image and the post-event image. Let's see the details describing them a bit, because I do not know how trained you are to near-infrared false color. So this image is called near-infrared false color. It's called false color in the sense that we are not used to these colors, so they look false to us. The true colors are the ones that we are used to, so vegetation should look green. Here is how water looks like. So water looks blue in true colors and looks much darker in near-infrared false color. Usually it's black, bluish black, something like that. You have that the urban areas or bare soil look cyan, or this greenish color. And you have that the vegetation is red. It looks brighter red where the vegetation is healthy, or let's say brighter green. So for example, grass looks brighter than a forest. A forest of conifers looks brighter than a forest of pines, okay? So depending on the type of vegetation, you have different shades of red in the case of the infrared false color representation. And what you can see here quite evidently is how the vegetation looks different in the post-event image. This could be visible also in the true color representation, but it's much more evident in the infrared false color, because in this case you see that the red has disappeared. If you remember the distinction that we have made before between the different products of crisis maps that we can produce, for a delineation map we would need simply to draw the perimeter of the burnt area. In case of a grading map, we need to try to make grades, so to see how severe it was, the burning effect over that area. So depending if some red is still a bit present, so if we have still some red components, some healthy vegetation, we can make different grades. We can use some tools, some semi-automatic tools, some processing in order to help us, because of course in this case it's not requested to the operator to manually draw the perimeter here of the burnt area, because it would be too difficult. Okay. So what can we use for helping the operator in detecting the burnt area? You have discussed with Professor Gianinetto the NDVI, which is a spectral index, which is called the Normalized Difference Vegetation Index, which is given by the difference between green and near-infrared band divided by the sum of these two. So it's a band ratio which can be easily computed with the QGIS or whatever image processing software you're using, and which provides information about how much healthy vegetation we expect to have in every pixel. Of course, this is an approximation, but combining this with the pre and post event comparison and the experience of the operator, we should be able to detect where the burnt areas are. And this is what you are going to make in the exercise this afternoon. Here, instead of showing a burnt area, I have decided to put an example of a global map of NDVI index, because NDVI is not used only for detecting burnt areas, and instead of doing this, I wanted to show you how you could exploit the NDVI to know how much of healthy vegetation you have in general, okay? Then combining, as I said, combining the pre and post, you can understand what happened, so where the vegetation has disappeared. It's very interesting. I think that you could exploit this in particular for some purposes with the students. There are very interesting websites providing information about the distribution of the NDVI over the Earth. Some of them allow you to move the Earth and to move the time bar in order to be able to see how things change over time. They could change with respect to season, or they could change with respect to the years due to the drought effect, the unfortunate situation that the vegetation is disappearing in certain parts of the Earth, or you could use it to see what's happening to the Amazon forest, for example. Okay, then we need to produce the crisis map. So here you see another example of crisis map. Again, I have put the legend here with the destroyed, highly damaged, negligible to slight damage detection. You can see here also possible damage, which is detected with respect to buildings, and also other details which are represented in the map. Okay, part of the lecture, and again, if you have questions, please, let's try to make this as much interactive as possible. So now we are going through a bit of discussion with respect to another type of disaster, which is floods. So what should we pay attention to if we want to map a flood, and which types of satellite images we should use? So in case of a flood event, the idea is to find on the map which are the inundated areas. So first of all, the definition of flooded area should be made. And this is important to take into account that what is flooded is not what is considered permanently covered by water. So our flood map should not include permanent waters such as lakes or rivers. So how can we get that information? We need to access other maps showing which are the rivers or the lakes insisting over the area of interest. Or again, we can take advantage of pre-event image, so that seeing where water is present with respect to the pre-event image, we can assess the presence of not normal water, so water which is due to the flood. Here you see in this image an example in which you see the permanent waters, which are represented in dark blue, while the flood extent is light blue. So where the water is present but shouldn't be. Again, as we have seen, detecting the water in the pre-event image or post-event image could be not so easy. We need to take advantage of semi-automatic processing in order to help the interpreter to correctly map what is visible. In the document that I have provided, that we have provided in the form of this electronic book with hyperlinks, you can see that I have put a small box with respect to SAR imagery, so synthetic aperture radar imagery, which is not part of this course, because this course, I think, is already overcrowded with many topics. We couldn't touch everything. What you should know is that flood often is mapped with another technology of satellites, which is not optical satellites, which is based on a completely different technique, which is based on completely different types of images. and which is often used for detecting floods. One of the reasons why this is used is because that type of technology is able to be not affected by the clouds. So you can take SAR images even if you have the area which is covered in clouds. While you see, for example, in this map that these white parts are marked as not available because covered by clouds. And as you can see, you have cloud and cloud shadow, because clouds produce a shadow in the field, which affects the visibility on the satellite image. So if you have clouds, both clouds and cloud shadows do not allow to map what you have below. So with SAR imagery, you have that huge advantage. And another advantage is that SAR images allow to see quite easily, and I put this under quotes, the presence of water, because water looks dark in SAR images. But please be patient for the fact that I'm citing this for the sake of completeness, because otherwise it would seem that I forgot a huge important part of flood mapping. But this could not be treated in the framework of the course because it would be too complex and too much. But consider that you have also this possibility. We are going to talk in this presentation only about flood mapping with taking advantage of optical imagery with the limitations that we have just discussed. And we are going to talk how we can detect floods over optical satellite imagery, thanks to the tools that, again, you have used and studied with Professor Gianinetto, and which are mainly the techniques which are used in practice for this type of processing, which is spectral indexing and satellite image classification. Actually, satellite image classification was not cited before for fire events, but it is cited in the documentation because it's an option as well. So you can use also optical image classification in order also to detect fires. In this slide, you see, similarly to what we have seen before, how different areas could look different with the NDWI this time, which has been introduced as well by Professor Gianinetto. This time we have another spectral index, which is called Normalized Difference Water Index, which is optimized, let's say, to detect the presence of water. So again, this is a spectral index. This is telling us how much water it is expected to have in the pixel, depending on the spectral response of water. And this is maximized using two bands in which we have a peculiar response of water. Again, the boundaries between the presence of water or not presence of water are not fixed. In the documentation, you will find some boundaries between water or not water, but these boundaries are not, let's say, rigid. It's the opposite. The boundaries between presence of water or not presence of water depend mainly on the experience of the operator. Sorry for that. So we need to rely, I don't know if the screen has disappeared in the meanwhile. It seems so. No, it's disappeared only for me. You're seeing this. Okay. It's based on the experience of the operator that we can set the boundary between what we consider as presence of water or not. That's why I have stressed, and I will still stress, that there is no automatic processing that can produce itself the map, let's say. The experience of the operator is essential. So even if an index like the NDWI is exploited, it is up to the operator to try to set this boundary between presence of water or not presence of water. And depending on where this boundary is put, you could have that you overestimate the presence of water, so you are putting water where actually you haven't, or you underestimate the presence of water, so you do not put water where it actually is present. So again, we do our best using the information that we have inside the satellite image. A great added value is provided by the experience of the operator, but of course, the maps will be affected by errors, as we have already discussed this morning. Here in this slide, you see an example of the difference between the dry season and the wet season, how it looks like on the optical image on top, and how it looks like in the NDWI representation. So here the colors represent the values of the NDWI with colors which remind you of the presence of water. So the values of the NDWI which highlight the presence of water are indicated in bluish colors, so that you can better interpret the presence of water. So thanks to the color representation of this index, the operator is helped in his interpretation. Here you see another example of satellite images of a flood event at different time frames, because again, this is another factor that we should take into account, that we have discussed also this morning when I have shown another flood map for a flood case, in which we saw that the date of the event and the date of the image were quite far, almost 1 week. No, maybe it was even more than 1 week. We have that the flooded area changes over time. We have that the water comes to the area and then goes away. So you have a peak of the flood in which you have the largest area which is affected by the flood. And depending if your image is taken before or after the peak, you will have different representations of the flooded area. And this is something that must be taken into account by everyone, by the map producer, but even more probably by the map user, so that they should check the date in which the map has been produced with respect to which satellite images, so to understand how to correlate that information with respect to what they experience in the field. Because of course, if in the field they are more interested in the peak situation, they should check if the map is representing that or not. Or if they are interested in the situation at the moment in which they are acting, they should take into account the fact that it could be an older situation which is represented on the map. And this is important. Another important factor is that the area looks differently, as you can see here, depending on the moment of the flood. You have here the largest amount of presence of water. This is the flood after a typhoon in China in 2018. And here you can see how different the area looks like. Here, probably in the lowest part, the majority of water is gone, but I think that we can still see traces of water in this area, because the fields are still very wet. Maybe they are not as flooded as they were here, but they are still very wet. And also this information is included into the satellite image. Of course, how easy it is to detect it, it depends on the spectral response of the field which is wet or not wet. So depending also on its nature, if the spectral response of that type of ground, when it is wet or when it is dry, how it is easy to be detected. Another factor that you should take into account when you want to map floods is that usually flood water takes lots of dirt and earth in it. So in this case, we see that it has a bluish color. Actually, you can see that it's different with respect to the normal. This is closer to the normal color of the water because it's where the flood is going away. Probably this is not yet the final normal watercolor. We would need here a prevent image, which unfortunately I couldn't find for this case. But what is important is that the flood color is usually peculiar. In this case, it's quite easy to be detected because, as I said, it's bluish, but sometimes it's more brown. So if you have brown water, it's not easy to detect the presence of brown water in the fields, for example. It could be misinterpreted with respect to what you have around. Again, what helps the interpretation is, from the one side, the visual comparison between the pre and the post event, and also from the spectral point of view, the exploitation of, for example, the NDWI, so the spectral index. So you can see here on the right how the inundated area was detected over these images thanks to the NDWI. So you see here that with the NDWI, it was marked that these were the flooded area, which with visual interpretation, we could even interpret it slightly differently. Okay, so again, the automatic processing or the semi-automatic processing is a factor which helps the operator, but which cannot substitute it. Okay. Another option for detecting the flood is to use supervised classification. So you have discussed classification during the remote sensing training. I remind you which are the basic principles of this. So the operator in this case is going to provide to the algorithms some samples over the satellite image that he has to recognize as belonging to a certain class. So in this case, if we want to detect the water, the operator has to select on the image some samples of pixels which correspond to water and to all types of water that he wants to detect. Because, for example, you have that as we said, you have also dirty water, water filled with dirt, which looks brown, for example. So you should be able to detect all shades of water. So the operator should be able to detect all possible types of water that he's expecting to be detected over the image in order to draw the flooded area. Here you can see with different symbols that which are the sets that have the samples that have been taken by the operator for the flood training, but also for the flood testing. You have discussed about the confusion matrix. You have discussed the fact that it is necessary when you perform a processing to be able to measure how good it is. So a way of measuring it is to, for the operator to select two sets of samples, one for the training and one for the testing. To the algorithm, only the training sample is provided in order to perform the classification. And then with the other set, which was, let's say, taken aside, the test is made. So the check of how good the classifier was in selecting the proper pixels which were similar to the training set, because I remind you that making a classification means to group the pixels of the image which are similar one to the other, and in order to do that you need to provide this sample, and the algorithm is going to look for other pixels of the image which are similar to those. The other pixels, the test sets, which are left aside, are compared with the classified image in order to see if the sample tests have been correctly classified. And that gives a measure of the quality of the classification. Of course, depending on how good was the operator, again, thanks to his experience in selecting the test sets, it could be a more reliable or less reliable measure of the quality of the classification. Because imagine if I take very easy to be classified pixels as test, so all inside a large flooded area, it's very likely that my test will be successful. If I'm able also to choose some tricky situations, some pixels which are very close to other pixels of other classes, so in more critical situations, then it will be more, or maybe with colors of water which could be more difficult to be detected in an automatic way, because my brain in some cases is better than the automatic classification, because I can understand when the water has a different color because of other factors, but it is still water. Okay, it could be also the opposite. It could be that my eyes are not able to see some differences, but the spectral information which is in the satellite image, it allows to detect the water. So it's a good combination of the visual interpretation, the experience of the operator, and the capability of the algorithm to detect pixels which are similar to the samples, allows to detect the flooded areas. Here we see another example of flood map. Here we see the water extent on the on 2 different dates, so you can see again how the water presence can change, and for some events it can be the user to ask for the monitoring of an event. So the Copernicus service, for example, can be activated for monitoring the event, so not only acquiring the first available image, but also to consider acquiring additional images afterwards in order to check how long the water is staying and in how large territories. In this case, you see that the water extent was collected with radar imagery. So this is not performed with optical imagery, which is what I anticipated, the fact that we are going to explore only a part of the possible processing which is done for floods, because the other part could not be treated into this course. Another point which is really important, and which again we cannot treat in this course, but I want it to be clear that it is a very crucial phase, is the crisis map validation. So every map, every data must be checked before providing it to the user. You probably know that if a map is produced in a normal situation, it has to pass quality control and validation before being, let's say, paid by the user and used by the user. In case of a crisis map, of course, this is a bit more difficult, because validating the map would mean to go in the field and check the quality of the map. Ask for field data, collect information, go in the inundated areas, go in the burnt areas, and to check in practice if what is marked as flooded or burnt in the map is actually what is marked is burnt and flooded in reality. And on the opposite, if there are parts that are flooded or burnt which are not marked as such in the map. But this would require to send a team in the field during the emergency, when the emergency activities are on, and so this is not feasible in majority of cases. On the one side, because of the costs, and on the other side, because it could interfere with the dealing with the emergency. So the teams of validating the the maps could interfere with the teams who are rescuing people. So this is not feasible in the majority of cases. Copernicus has planned to validate at least a sample of the maps that they produce. They have dedicated some money to the validation because it's important, as I said, to know how good these maps are. But this is done on a sample basis. So every a certain number of cases, what is feasible to be mapped, to be checked, is checked in the field. Consider also that some events can be mapped even afterwards. So it's not necessary to send the people during the emergency. So some validations are done a few days after the peak of the emergency. For a fire, this is usually easier because the traces of a fires last longer, in particular if it is a forest fire, until the new vegetation is growing. You can see the traces of the fire. In case of flood as well, maybe the water is gone, but you can see traces of flood. You can see traces of flood in the fields because the fields are affected by the presence of water. For example, the high plants are laying down because they have been underwater, or you can have that you have traces over buildings because part of the walls are wet still. You can ask people. So there are ways of checking the quality of a map even after that the peak of the emergency has occurred. What is done for every map is quality control. This is done always. The quality control is done internally, and even in the case of Copernicus is done also by the Copernicus team, so that at least the major mistakes are avoided, so that the consistency, everything that can be checked without going in the field is checked. So the consistency of the legend with respect to the map, the symbols which are coherent, the presence of the overview map. Also, maybe some internal checks are done in order to produce the maps in parallel by more than one operator. There could be different ways of quality controlling the products before releasing them in order to guarantee a high value product. Okay, another section of the presentation is over, so if you have questions, it could be a good moment to make them. Otherwise, we can go on with the last part of this morning session, which is related to another part of the services of Copernicus EMS, which are the early warning and monitoring services. This is what I introduced at the very beginning this morning, the fact that in addition to these on-demand mapping services, there are permanent services, let's say, because the maps that we have discussed so far are produced only if someone asks for them. The services that we are going to mention from now on are services which are produced permanently. These are monitoring services which work on a semi-automatic procedure. Most of it is automatic, but of course there are operators overviewing them, which provide information about floods, fires, and drought. And here you see a schema that tells us how this can be introduced into the general emergency management of Copernicus. So the fact that these alerting systems can be used in order to alert the municipalities, the actors, the users, the civil protection, in order to for them to be prepared, in order to take the measures to lower the impact of the disaster, and maybe also to later on trigger the on-demand mapping. So this is how these services are designed in the framework of the whole service. Now we are going to introduce fast all these services. If you are interested, you can go to the links that are provided both here in the slides and in the documentation of the ebook in order to explore the services and check what is available. So all these services have, let's say, two different types of information. The information which is related to the early warning and information which is related to the monitoring. So the early warning is visible partially on the website, but in particular it is actually a service which is activating the users who ask for it. So if I am a municipality who feel threatened by a flood or by a fire, I can, through the civil protections, through the national users, authorized users, I can make a request to the service in order to be able to access this early warning, so that I can receive as a mayor, for example, an SMS or an email in case of a threat which is coming for my municipality. And this is a service that you as a common user cannot see, but which is available to certain authorized users. But what we can see as common citizens, if we access the platform, is anyway where the let's say, actual in the sense that what is happening now, services are visible, which warnings are active at this moment. And we can see also which are the events that occurred in the past, so the monitoring. It's a complex thing, this service, because it involves the exploitation of meteorological data, as well as satellite imagery. You have studied a bit more into detail the imagery which is coming from the Sentinels, which has a revisiting time of 1 to 2 weeks. So we are talking about weeks. But we have other satellites which are monitoring the Earth much more often. For example, the MODIS satellite, the MODIS sensor, which can allow to obtain daily images of the Earth, which can provide information about the presence of water, the presence of fires, the presence also of active fires. Thanks to the thermal band, we can see also where we have something which is hotter than expected, so probably there is a fire going on. So these spectral information and the automatic processing, and the fact that these images can be acquired automatically every day, allows to monitor these phenomena. Here you see a screenshot for one of the first service that I'm going to present, which is the European Flood Awareness System, which acronym is EFAS. There are two services, one dedicated to Europe and one dedicated to the whole world, which is GLOFAS, Global Flood Awareness System. So these two services are very similar one to the other, but one is dedicated only to Europe and the other one is dedicated to the whole world. In this service, you can have information about the flood probability. Here you can see in less than 48 hours or more than 48 hours, the mapping of rapid floods. But you can have also many more details. You can also access the information about the past events. So you can have lots of details with respect to floods. These services can be used both inside the web interface of the service, so accessing it with your browser, but you could also access it through QGIS, for example. You can load the service into the GIS software so that you can overlay these the layers coming from a service to other layers. Of course, this is not something which is included into the training this afternoon because it would be too much, but consider that this is also an option. Here you see an example of the interface of GLOFAS, so the same service with respect to floods, but dedicated to the whole world. And here you can see some of the layers that can be displayed. So accumulated precipitation, precipitation probability greater than 50 millimeters, where you have the points reporting information, and also 20-year return period exceedance. So probability computation about the return period of certain levels of flooding. The first two, so where the warning and monitoring services with respect to floods. We have equivalent services with respect to fires. The European version of the service is called EFIS, European Forest Fire Information System. Here you see the web interface. You can see that in the web interface you can select different types of background layers, such, for example, the human settlement layer that will be introduced this afternoon during the practice. It's information about the presence of buildings, automatically extracted from satellite imagery. The land cover, the Corinne land cover, or protected areas. And you can also display the damage assessment due to fire in the last day, or in the last 7 days, or in the last 30 days, or along the fire season. But you can also, with this calendar here, you can select the area, the period of interest. So you could see also events that occurred in the past. A similar interface is provided for the service for the whole world. In this case, the service is called Global Wildfire Information System, or GWIS. Again, this is provided continuously with information about ongoing fires. Fires occurred in the very few past days, but also much more in the past. From the website, you can also access other details coming from additional statistics which can be computed starting from all these data which are organized into a database. And the service itself provides statistics and graphs that can be computed. Here, for example, you can see the seasonal trends for a certain country or for a certain year. Or also in this case for GWIS, you can see for a country over the years how much of the area was burnt. These are automatic computations which are made over the database, which is, as I said, extracted from the satellite imagery, from mainly automatic processing of the satellite imagery. The last service that we are going to go through is the European Drought Observatory, which is an important service, which is providing information about the drought phenomenon, which we know is a very severe phenomenon which is occurring along the world, and which is mainly due to climate change, but also to not very wise use of our territory. And here we can see again the monitoring of this phenomenon thanks to the processing of satellite image. You can see here how it is represented in terms of rainfall deficit or soil moisture deficit, or an alert due to vegetation stress, which is following rainfall or soil moisture deficit. And so you can see how these services allow to not only see the critical situation, but also to monitor how it changes and it changed over time. The same service is provided for the whole world. It is called the Global Drought Observatory, and here you can see a screenshot of the information, and again here you can find a list of the indicators which are provided in the website, which are precipitation, soil moisture, conditions of vegetation, hydrological stream flow, and temperature. Okay, this is all from my side. I hope that this was interesting, as an example, of course, it's only one example of what you can get from satellite and GIS data processing. You are going to touch with your hands some of these processings this afternoon during the practice. If you have questions, you're